In this video, I'll be presenting my paper, Data Structures for Deviation Payoffs, where Eric Brinkman and I developed new ways of representing symmetric games that allow for much faster computation of Nash equilibria. The presentation is based on the talk I gave at AAMAS, the Autonomous Agents and Multi-Agent Systems conference that took place earlier this month. A symmetric game is one where all of the players face the same incentives. A huge fraction of the games that we use to teach game theory, like Prisoner's Dilemma and Rock, Paper, Scissors, are symmetric, meaning it doesn't matter if you're player 1 or player 2 in these games. And in a symmetric game, all of the payoffs below the main diagonal are redundant with ones above it. And likewise, in cases where multiple players choose the same action, we don't need to represent that payoff multiple times. And this redundancy gets worse as the number of players in the game increases. In the payoff matrix representation, if a game has P players and each player has A actions, then the payoff matrix has A raised to the P cells. But if the players are all symmetric, instead of this representation that grows exponentially in the number of players, we have a number of unique profiles that grows combinatorially in the number of players and actions. So for example, in the Prisoner's Dilemma, we can store all of the relevant payoff information by keeping track of each of these symmetric profiles that say how many players choose each action. And then, for each of the actions played in that profile, we can store the payoff those players would get. And if we think about increasing the number of players with a fixed number of actions, a profile-based representation can provide exponential savings relative to the payoff matrix. And so we want to represent symmetric games using some sort of profile-based representation, but we need to make sure that that representation facilitates efficient deviation payoff calculations. We define a deviation payoff as the expected utility a player would get if they deviated to a fixed action, while everyone else randomized according to the same mixed strategy. And then the deviation payoff vector gives the expected utility for deviating to each of the individual actions. And the reason that we care about deviation payoffs for symmetric mixed strategies is that in a symmetric game, we search for symmetric equilibria, and if we can compute deviation payoffs for any mixed strategy, then we can run a number of different algorithms for finding Nash equilibria. And if we can also calculate the partial derivatives of the deviation payoffs, we can run additional Nash algorithms. So in this paper, we present a number of data structure optimizations that each help to accelerate the deviation payoff calculations, and the total effect of all of these optimizations is a very large speedup in Nash equilibrium computation. Throughout the video, I will use as a running example deviation payoff calculations for the mixed strategy 0.2, 0.3, 0.5 in this symmetric game. This game has 4 players and 3 actions, and I've chosen it mainly because it's the largest game that I could fit on a single slide. This will help to illustrate the various data structure optimizations, but it's worth keeping in mind that this game is small enough that we could operate on the full payoff matrix if we needed to, and the optimizations we provide make a much bigger difference in much larger games. One thing to note about this game is that the payoff value 6 occurs 12 different times, but all of those correspond to the same symmetric profile. And so if we switch to a profile-based representation, we'll have only one instance of the payoff 6, corresponding to the profile where one player chooses the first action, 2 players choose the second action, and 1 player chooses the third action. And in that profile, the player choosing the first action gets a payoff of 6. So this approach of representing symmetric games by mapping profiles to payoffs is well known, and this mapping can be stored in many different data structures. In the Gambit action graph game library, this sort of mapping is stored in a prefix tree, and in our previous implementations, we've stored it in a dictionary. But the first optimization we can do is hinted at by the way I've lined up all of these profile and payoff vectors, and that's to squish all of the profiles together into a matrix. So now we have an array containing all of the profiles and another array containing all of the payoffs, and any given column in the first array corresponds to a profile vector, while the column at the same index in the second array gives the payoffs for that profile. And in some programming languages, this switch can already be a big help because it lets us vectorize many of the computations. But looking at this payoff array immediately suggests room for further improvement because we have a bunch of invalid entries in the payoff table. For example, in the profile where one player chooses the first action, nobody chooses the second action, and 3 players choose the third, there isn't a valid payoff entry for the second action because nobody is playing it. And so when we do calculations with these arrays, we end up having to mask out all of the invalid entries, but we can avoid that and also get a more compact representation by switching our perspective from storing profiles to instead storing opponent configurations. So here, our first array stores in any given column a possible configuration over the p-1 opponents. Whereas before, the profiles all summed to 4, the number of players in our example game, they now sum to 3, the number of opponents any player would have. And so the payoff 6 now happens in the case where no opponents are playing the first action, 2 are playing the second action, and 1 is playing the third action. And if against that opponent configuration, the player chooses the first action, then they'll end up in the profile 1, 2, 1, and they will get a payoff of 6. And so that payoff gets stored in the row for the first action against that opponent profile. Meanwhile, the other rows within that same column correspond to other profiles, because if the player were to choose the second action, then this -3 gives the payoff of playing action 2 in the profile where 3 players play action 2 and 1 plays action 3. So this representation is more compact than storing profiles, and also makes it easy to vectorize the deviation payoff calculations. So let's go through that computation now. In the deviation payoff calculation, we will be summing over all of the configurations the payoff value in that configuration times the probability that that configuration occurs under the mixed strategy that we're given. And the first step in that probability calculation for any given profile is to multiply out the probabilities. And we have to do that calculation for every profile, and we can do that by broadcasting exponentiation across the configuration dimension of our first array. Now we need to multiply those probabilities over the actions, and so we'll take a product down the actions dimension, and this gives us a probability for each configuration, but that probability has not yet taken into account the number of arrangements of the opponents that could result in the same symmetric configuration. And so we have to multiply by that number of asymmetric repetitions corresponding to a given symmetric configuration. And we'll come back to how those repetitions are calculated in a moment. But that product now gives us the probability of each configuration occurring under the symmetric mix strategy. From here, we need to multiply the probabilities that we've calculated by the corresponding payoff values, and that can be done by a broadcast down the action dimension of the payoff array. And now that we have weighted each payoff by the probability that it will occur, we just need to sum over all of the configurations. When we sum over the configurations dimension, that gives us a vector of the deviation payoff for each action, which is what we need to calculate a Nash equilibrium. To compute the number of asymmetric repetitions of a given symmetric configuration, we are counting the number of ways we can assign the symmetric players to the different actions to give us the same configuration. And so if we had 10 opponents and 4 possible actions, then for the configuration where 3 players play the first action, 4 play the second, 2 the third, and 1 the fourth, the number of arrangements would be given by the multinomial coefficient 10, choose, 3, 4, 2, 1. The multinomial coefficient generalizes the binomial coefficient to the case where there's not just in the set and out of the set, but rather several different places where the elements could be put. And we can compute it by the factorial of the number of opponents divided by the factorial of the number of opponents assigned to each action in the current configuration. But because this number of repetitions depends only on the configuration and not on the mixed strategy that we're currently evaluating, this is actually something that we can compute once in advance and store. And then, since we need to compute deviation payoffs many times over the course of an equilibrium search, we can avoid recomputing those repetitions on each deviation payoff calculation. So the third variant of our data structures stores another parallel array where for each configuration we save the number of repetitions, and then we can just use that each time we compute a deviation payoff. But actually we can do even better, because even though the repetitions are logically part of the probability calculation, by associativity, we can move the parentheses and multiply the repetitions by the payoffs, and since nothing in this set of parentheses depends on the mixed strategy, we can do this multiplication in advance. So, if we pre-multiply the payoffs by the number of repetitions, this gives us a repetition-weighted payoff array, and we now don't even need to store the repetitions because they've been pre-multiplied into the payoffs. So we're back to storing just 2 arrays, and when we calculate deviation payoffs, we can skip the steps of finding the number of repetitions and multiplying by them. And at this point, our data structures are efficient enough to store and work with some very large symmetric games. But that runs us into another problem. Namely, this number of repetitions can get absolutely enormous. If we consider a game with 33 players and 5 actions, among the configurations we need to store is one where the first 3 actions are all played by 6 opponents and the last 2 are played by 7 opponents. And for this configuration, the number of repetitions is larger than we can store in a 64-bit integer. And so for all of the games in the orange region of this plot, there is at least one profile where the number of repetitions overflows a 64-bit int, and so with standard CPU arithmetic, we can't actually calculate correct deviation payoffs. To deal with this problem, we use the standard approach from probability calculations of working in log space. That means we'll need to take the log of the repetition-weighted payoffs, but in this case, that would give us lots of invalid results when we take the log of a negative number. But luckily, the incentives we represent in game theory are invariant to positive affine transformations, which means we can rescale the payoffs into any range we want, so we'll just pick some fixed positive range to rescale our game's payoffs into. Here, I've scaled them from 1 to 1,000. And then we can take the log of the repetition-weighted payoffs, putting us into log space. To do our deviation payoff calculation in log space, we first need to take the log of the mixed strategy, and then this exponentiation becomes multiplication, which we broadcast over the configurations dimension. Then, instead of a product, we'll take a sum down the actions dimension, and we don't need to worry about repetitions, because our payoffs are already weighted by repetitions, so we just need to add down the actions dimension. And now comes the point where we want to sum over the configurations, but that sum can't be done in log space, so here we need to do element-wise exponentiation to get us back into our fixed payoff range, where we can now sum over the configurations to get the deviation payoffs. Of note, these deviation payoffs are in the rescaled payoff range, and in principle we could undo our affine transformation to put them back into the game's original payoff range. But it's actually better to wait until we're done computing Nash equilibria and only transform the payoffs at the end before we present them to the user, because keeping a fixed range of payoffs also helps in tuning the hyperparameters of our equilibrium computation algorithms. And now that we've turned our entire computation into a simple sequence of broadcast and reduce operations, all of this can be easily moved to the GPU for further acceleration. And once we're working on the GPU, it becomes feasible to perform deviation payoff calculations on a batch of symmetric mixtures at the same time, which we can use to run several different equilibrium searches in parallel. The net result of all these optimizations is a roughly 10,000-fold speedup in the time to compute deviation payoffs, as well as in the time to run Nash equilibrium searches. And this means both that we can operate on games with many more players than was previously possible, and that we can feasibly run slower equilibrium computation algorithms and still expect results in a reasonable amount of time. With our data structures, we've found that the most effective way to compute as many Nash equilibria as possible in a large symmetric game is to run many instances of replicator dynamics in parallel from different initial mixtures, and also to run many instances of gradient descent in parallel from different initial mixtures, and then to combine the sets of equilibria found by replicator dynamics and gradient descent. We recommend this approach because the complete algorithms that are guaranteed to find an epsilon Nash equilibrium are dramatically slower and can't really be run on large games in practice. But replicator dynamics runs very fast, and if we initialize it from many different initial points, it's likely to find a few Nash equilibria. And even though gradient descent is generally slower than replicator dynamics by roughly a factor of the number of actions in the game, our data structures are efficient enough that running gradient descent is often feasible, and we generally find that replicator dynamics and gradient descent find only partially overlapping sets of equilibria, and so we can get more Nash equilibria by running both and taking the union. In the paper, we also show how to calculate the Jacobian matrix of partial derivatives that's needed for gradient descent and some other algorithms. And we also discuss extensions of our data structures to other types of games, such as role-symmetric games, where players only have the same incentives as other players in the same role, and action graph games, which can be even more compact than symmetric games under certain circumstances. It's likely that there's room for further optimization of the data structures and algorithms for symmetric games, such as using CPU multithreading. And with our data structures, lots of new directions become possible, including generating better random games for evaluating game theoretic algorithms. And while our code is open source, we would love to see these data structures implemented into Gambit or other more general game theory libraries. In the description of this video, I'll include a link to the paper on arXiv, as well as links to the Julia library with the code from this paper, and the Python library with a better user interface to some of these data structures. And if you have any questions about our paper, I'd be happy to try and answer them in the comments.